Let's talk about quantum chemistry. Consider this lecture an introduction more than the full entourage of quantum chemistry. This topic is actually rather large and full of interesting concepts, but because this is an intro class, we're going to go a little bit more slow about it. The culmination of the lecture will rely on being able to derive the electron configurations of atoms and ions. So let's start by talking about what quantum chemistry is all about. Ultimately, the idea of quantum chemistry has to do with the concept of waves. And a wave, as you can see here, is simply an oscillating pattern that repeats itself multiple times in the course of a transgression. This transgression, transposition, whichever way you want to refer to it, has to do to some degree with time, as you'll see in a second. But just to give you an idea, when we talk about waves, and you may recall this from your algebra, maybe trigonometry days in high school, um, when you talk about a wave, we can actually refer to the wave in terms of the degrees in radians associated with the wave, right? So you could go from 0 to 2 pi, and that describes a full oscillation for your wave as it goes through a crest all the way down to a trough and back to the origin. Alright, so that 0 to 2 pi is your usual unit circle that describes the wave. Now the number of cycles that you can process in 1 second is what we end up calling the frequency. And the frequency is something characteristic of waves. Basically kind of like the name implies. How frequent is this completion of oscillation pattern going to take place in terms of the 1 second time. But in addition to that, there's something else that's of importance when describing a wave, and it's called the wavelength. And as the name implies, this is the length from crest to crest within your wave. And if you look carefully, yes, and we also use the symbol lambda to represent the wavelength. But if you look carefully, crest to crest in terms of radians, it means that you're going from pi over 2 to 5 pi over 2. And if you subtract those two, you're going to get 2 pi, technically speaking. So technically, 2 pi ultimately ends up equaling the wavelength. Now that's more important for transformations that allows you to describe the wave in terms of distance from the point of view of an angle. But the thing that's going to be most important to us is the fact that the wavelength is a measure of length. It's the length of the wave, but it is a measure of length. And frequency, on the other hand, is a measure of inverse time. And so when you multiply the wavelength by the frequency, you end up getting units of length over time, such as meters per second or miles per hour, and those are the units of speed. Now the wave that we're going to talk about here exclusively is light waves. And as such, the speed that we're looking at right here by multiplying the frequency with the wavelength is known as the speed of light. Another corresponding relationship that we're going to look into has to do with energy. The frequency, if it gets multiplied by another constant known as Planck's constant, this particular multiplication derives the energy of a light wave. It also gives you the energy associated with certain atomic processes, quantum processes. But the idea is pretty much this. Yes, c is the speed of light, h is Planck's constant, and the speed of light is equal to 2.998 times 10 to the 8 meters per second, whereas Planck's constant is 6.626 times 10 to the negative 34 joules times second. Now, future calculations, I'm going to provide you with those numbers. Basically, you need to know is that C stands for 2.998 times 10 to the 8, and H stands for 6.626 times 10 to the negative 34. All right, and as a result of this, notice that because C equals frequency times wavelength, the frequency can be regarded as the speed of light divided by the wavelength. And now if we look at the equation that down here, Planck's equation, simply substitute the frequency in terms of wavelength and you end up with a new version for energy, namely that hc over lambda equals energy. And which version of the equations you end up using depends on what you have been given to begin with. If you have frequency, then it's most convenient to find the energy by using this equation here on the bottom left. If you have frequency, you could use the equation here on the upper left to find the wavelength. But if you do have wavelength, you want to use the second, the last equation here on the bottom right. All right, so let's take a look at a quick example. Oh, the other thing too is that the units of frequency are per second, okay, or second to the -1. The units for wavelength, on the other hand, will have to be in meters. And the reason for that is because speed of light is in meters per second. So when you use the equation here or even down there, the wavelength needs to be in meters, so that you end up with meters times 1/second, which is meters per second. All right, so let's take a look at a quick example. We have a photon of light with a frequency of 3.25 times 10 to the 13 per second. What is the wavelength and energy of this light wave? All right, so first things first is we recognize that we have been given the frequency. So we need to solve for everything in terms of frequency. So starting with the speed of light equation, we solve for the wavelength, divide the speed of light by the frequency. And over here, we can simply just use the Planck constant multiplied by the frequency to yield the energy. Alright, so with the first equation, we plug in the speed of light, 2.998 times 10 to the 8 meters per second. Underneath here, we plug in 3.25 times 10 to the 13, 1 per second. And when you perform this calculation in your calculator, you must use parentheses. If you don't use parentheses, it's very likely that you'll end up with the wrong answer. So enter open parentheses 2.998 times 10 to the 8 close parentheses divide by open parentheses 3.25 times 10 to the 13 close parentheses and then press enter. You should find out that yes, seconds cancel out, but more importantly that you end up with the following answer. And I would recommend that you do this calculation with your calculator and make sure you get the same value that I got. If you don't, if you're getting a different exponent, that's probably because you forgot to use your parentheses. Alright, and down here, to get the energy, we multiply 6.626 times 10 to the -34 joules second times 3.25 times 10 to the 13 per second. The seconds are going to cancel out, and you're going to end up with just joules, specifically 2.15 times 10 to the -20 joules. The last thing I'll say is that if you have a problem where you start with wavelength, if the wavelength is not in meters, then you have to change it to meters. And that's where dimensional analysis will come in. You could be giving a wavelength in nanometers or picometers or micrometers. You have to change that to regular meters. Alright, now another aspect of quantum mechanics that we really can't dwell too much in detail, but I need to describe it so that you understand what's going to be happening when we describe the electronic configuration of the atoms, is that there are ways of describing the waves associated with the nature of interaction between the electron and the nucleus of an atom. And technically speaking, that wave equation has three parameters that describe it in terms of where it is from the point of view of the nucleus. There is the radius, which is the distance from the nucleus to the electron, and then there are these angles, which basically tell you where in space, in 3D space, the electron is positioned. Now, each one of these functions can be subdivided into each individual function with that specific parameter as the only variable, and multiplied together they give you the overall wave function. When you apply this to the true equation of quantum mechanics known as the Schrödinger equation, you actually end up spelling out certain quantum numbers, which are supposed to be whole numbers that depict energy levels like the ones that I'm showing right here. The lowest energy level is the first energy level, followed by the second, followed by the third, the fourth, and so on and so forth. And what ends up happening here is that the electron resides in either of these energy levels, but the one that's closest to the nucleus is the one that is at the lowest energy, because the closer your electron is to the positively charged nucleus, the more stable it will be. Now, let's say that you have light that's interacting with this element. What happens is that if the energy of light matches up with the energy that it would take to move this electron from the lower level to any of the higher levels, energy level 1, energy level 2, energy level 3, 4, 5, basically you will undergo an event known as absorption. During absorption, the energy of light gets completely taken up by the electron, and it's being used up to basically carry out this potential energy event, this work of moving the electron from lower energy level to higher energy level. And the equation that describes that event is the one shown here. The changing energy, which will have to be in joules, is equal to negative B times 1 over m final square minus 1 over n initial square. This is known as the Balmer-Rydberg equation, or the Rydberg-Balmer equation, and the value of B is 2.18 times 10 to the negative 18 joules. If you are undergoing absorption, you will be moving from a lower energy value to a higher energy value. So N final is going to be greater than N initial in this equation. And also the energy that you will obtain will be positive. But if you actually undergo the opposite process, you go from a higher energy state to a lower energy state, you will actually be producing energy, and the element will emit light. We call this emission. And in this particular case, M final will have to be lower than N initial. That's that giveaway that emission is happening. You still use the same equation, but the overall energy ends up being negative at the very end, meaning that you lost energy in the form of light. So I'll have you do some of these calculations in the future, but to give you an idea of what you're kind of looking at, you have the light spectrum, which comprises gamma rays, which are the ones with the lowest wavelength and by default the highest energy and frequency, and you go all the way to radio waves, radio waves, which are the ones with the longest wavelength. And basically what you have here is the gamma rays, X-rays, ultraviolet rays, then the visible spectrum. Between the ultraviolet and the visible spectrum, you have the boundary of the violet light. And between the infrared and the visible spectrum, you have the color red as the boundary. After that, you have microwaves and radio waves. Now, narrowing down on the visible spectrum, which is what we get to see as the colorful aspect of light, you can go from roughly 400 nanometers up to 800 nanometers. And if you convert the wavelength to frequency using the speed of light equation, you'll find out that the values in the visible region go from 7.49 down to 3.75 times 10 to the 14 hertz. You will also find out that if you use Planck's equation, that the energy lies between 4.97 and 2.48 times 10 to the negative 19 joules. And if you convert this to kilojoules per mole, you'll find out that the value falls between 299 and 149 kilojoules per mole. Alright, so using the Rydberg-Balmer equation, the value you're going to get for energy is in joules specifically. And all you have to determine is what's the final state and what's the initial. Now, for the hydrogen atom, if N final is equal to 2, and you're undergoing emission, meaning that N initial has to be larger than 2, what's going to happen is that you're going to end up producing light of a very specific magnitude. So if you start with a value of 3 for N initial, right, and go to 2, you'll get negative 3.03 times 10 to the negative 19 joules. And you might want to do that calculation just to kind of make sure that's the case. If you start from N initial equals 4 down to 2, you get negative 4.09 times 10 to negative 19 joules. If instead you start with N initial equals 5, you'll end up with negative 4.58 times 10 to negative 19 joules. And if you start with N initial equals 6, you'll end up with negative 4.84 times 10 to 19 joules. Now the thing to be of notice is that everything is times 10 to negative 19, times 10 to negative 19, times 10 to negative 19 joules. And you're ranging between 3.03 and 4.84. And if you look carefully, 3.83 and 4.84 falls completely in between the visible spectrum, meaning that all of these transitions from higher energy levels down to the second energy level in particular yields visible light being emitted from your elements. And so when you look at like neon signs, for instance, that shine, that like pink color, blue color, what you're basically seeing is atoms of neon being excited with electricity, and that excitation allows the electrons to go to a higher energy level. But then when the electrons come back down, they fall back down such that um, you end up producing visible light, and that visible light is the light that you see as the lights proceed to light the venue, whichever it may be. All right, now second thing I want to tell you in regards to this, for hydrogen, n initial could be any value higher than 2, but n final is going to be equal to 2 for you to produce visible light. And when n final is equal to 2, this is known as the Balmer series. So you may actually hear me say, or you may actually see in problems, call for you to calculate the emission of light where n initial equals, whatever, it could be 7 within the Balmer series. And that name itself will imply that n final is equal to 2. After that, you could be asked to convert the energy to frequency or convert it to wavelength. So just be aware that those equations will still apply, in addition to changing energy equals negative B times 1 over n final square minus 1 over n initial square. All right, now what happens with this rather simplistic equation is that it actually predicts something that wasn't completely understood at the time, and it was the fact that the elements would emit specific energy values of light, specifically wavelengths of light, and it wouldn't be a continuum, it would be a very specific value. And with this equation, that ultimately has to do with the idea that the electron is interacting with the nucleus in the way of a wave, is what allows the prediction to match up the observation, the experimental observation. So this particular aspect of quantum mechanics is pretty cool, pretty enticing, in fact. All right, in the next video, I'm going to talk to you about what the interaction is between the nucleus and ultimately the periodic table and all these atomic and quantum numbers. The last thing probably I should tell you is that when you look at the energy levels that we just discussed in terms of absorption and emission, they actually sort of match up with the row number in the periodic table. But I'll continue that discussion in the next video. So see you then.